hazardous locations and the IEC. Part 1. IEC, the road to harmonization. The science of fire and explosion can be quite complex, but the underlying principles are really very simple. Bringing together a flammable material or fuel with a source of ignition in the presence of the oxygen in the atmosphere will result in combustion. Depending on the particular mix, the combustion can be a slow and mesmerizing fire or a rapid and all-enveloping explosion. Since the earliest days of harnessing the energy available from the commercial development of petroleum resources, understanding the science of fire and explosion has been critically important. Advancement in the process industries that deal with the extraction, refining, and transformation of petroleum, as well as a wide range of other flammable manufacturing materials, has created an ever-increasing demand for controlling the flammability risks. One distinct area of concern has been that electrical equipment and its wiring could provide the source of ignition for explosive mixtures. Thoughtful engineering analysis, techniques, and specialty equipment would ultimately be required to effectively manage these risks. Over the years, many industrialized nations worked within their own economies to develop a national consensus on how to evaluate and classify the risks associated with the extraction, processing, and handling of flammable materials in the presence of electrical systems. The United States, often in collaboration with Canada and Mexico, developed a comprehensive set of rules for evaluating and classifying the risk of ignition from electrical sources in those areas that could have explosive atmospheres. This activity also produced regulations for the techniques and equipment to be used for these installations. They were then firmly aligned with the specialized product standards that were simultaneously being developed by consensus among industry engineers, technical committees, and third-party certification agencies. The North American approach for classifying the explosion and fire risks in these hazardous locations, frequently referred to as the class and division method, has been collected into a chapter of the National Electrical Code, or NEC, as well as corresponding Canadian and Mexican codes. Meanwhile, there were also alternative methods being developed in other parts of the industrialized world for dealing with these locations. Certainly, the analysis of the actual risk of fire and explosion would yield the same fundamental results, regardless of approach. But it is the method of classifying the risks and the engineering solutions applied that would introduce additional options in the development of electrical systems. Even though the underlying science would be the same, application of the principles to real installations requires detailed technical knowledge of the standards, codes, and procedures that are unique to a specific national jurisdiction. But it was the growth of international corporations and trade, as well as political and economic reorganization in many regions, that created the need to effectively address crossover electrical installations. The ability to coordinate the methods for these installations in hazardous locations fueled the drive toward worldwide harmonization as an important goal. Historical evolution of the standards that would influence the future engineering of systems and the development of products for hazardous locations typically began at a national level. They then moved on to multinational collaboration that is ultimately expanding to yield a fully international framework. What is now known as the North American approach toward hazardous locations formed around a working consensus among the United States, Canada, and Mexico. The European movement along the path from national to continental standardization was driven by enormous shifts in commercial, political, and economic collaboration. Eliminating technical barriers to the free flow and application of equipment in the European community forced the standardization of products and methods to become an essential part of the plan. By 1978, the Committee for Electrotechnical Standardization, or CENELEC, issued standards for use across Europe to improve coordination and blending of those that had been developed by individual countries. The resulting Euro norm or EN standards made possible the creation of the ATEX directives that were issued to establish essential health and safety requirements across Europe. ATEX, an acronym from the French for explosive atmospheres, is divided into two parts. ATEX 137 covers the requirements for installation, maintenance, control, and safety procedures for users and employers in the non-electrical operation of their facilities. But it is ATEX 95 that addresses the responsibilities of manufacturers and importers of electrical equipment for use in explosive atmospheres. It affects the design, production, certification, declaration of conformity, quality controls, and audit processes for these specialized products. The International Electrotechnical Commission, or IEC, is a 100-year-old organization of more than 80 member countries, whose mission is to develop and publish electrical and electronic consensus standards and assessment programs. Their efforts are dedicated to eliminating barriers to global trade that could be caused by conflicting national standards. Largely based on the work of Senelec, the IEC created a series of standards for explosive atmospheres that have now been embraced in a revision of the Euronorm standards, including renumbering for consistency with the IEC documents. An additional effort toward international harmonization was the creation of a comprehensive assessment program that could be used for implementation. Known as the IEC EX scheme, it provides a structure for authorization of certification agencies, called notified bodies, to be available to conduct examinations of products and manufacturing processes. The notified bodies would also conduct evaluations of the manufacturer's quality systems and controls, including the scrutiny of follow-up audits. The all-important test reports and certificates of conformity issued by these agencies provide the documentation for product nameplates and marking. Support for global harmonization continues to grow. The UN, through its European Economic Commission, promotes and encourages adoption of IEC standards and the IEC EX certification scheme among the Commission's 56 member countries. And in North America, IEC standardization has also received validation. Although the United States, Mexico, and Canada may be at different stages, revisions to each country's national standards over the past several years have included the path toward harmonization. For the United States in particular, progress toward harmonization led to the adoption of two new articles in the National Electrical Code, Articles 505 and 506, as alternatives for treating hazardous locations. These articles are very much in line with IEC standards. Part 2. Treating the hazardous location. There is no doubt that challenges can always be lurking in the details, but a clear sense of the underlying principles for dealing with electrical equipment in hazardous locations can bring them to light. The fact that the science and much of the equipment theory and technology are so similar between North American and IEC systems makes resolving the points of difference quite manageable and the transition less difficult. Four crucial elements guide the overall process for addressing the use of electrical equipment in hazardous locations, regardless of the system used. The first, and most fundamental, is conducting a risk assessment. This is an evaluation of the degree of likelihood that an explosive condition could develop in a process area or other location because of flammable material in the atmosphere. The second consideration involves selecting the type of technology and specific equipment to protect against the potential for electrical components becoming a source of ignition. Installation practices will also help guide the selection once the risk assessment has been completed. Manufacturers are responsible for assuring that standardized testing, assessment, and certification of the equipment they have engineered and manufactured are accomplished, the third element. And finally, manufacturers must adhere to audited quality, marking, and documentation standards that make certain all relevant application and conformity data are available to specifiers, installers, and owners. Part 3. Risk Analysis for Gases and Vapors. Risk analysis involves measuring the prospect that there is sufficient flammable material in the atmosphere to create an ignitable mixture. Starting with gases, vapors, and flammable liquids, referred to as Class 1 in the National Electrical Code, the North American approach has traditionally divided the risks into two categories, reflecting the probability that an ignitable mixture could occur. The first, Division 1, includes locations where normal operations could permit the flammable material to form ignitable concentrations in the atmosphere, either some of the time or perhaps even all of the time. In contrast, Division 2 describes locations where hazardous materials are stored, handled, or processed in ways that are unlikely to create ignitable mixtures when everything is operating normally. IEC 679, the principal underlying standard for harmonization, uses a similar concept for categorizing risks, but it splits the risk of ignitable mixtures during normal operations into two separate categories. Calling the categories zones, the IEC approach starts with Zone 0, defined as those locations operating normally that could create ignitable concentrations of gases or vapors continuously or for long periods of time. Secondly, there is Zone 1. This zone could still be expected to create explosive concentrations during normal operations, but not often enough or long enough to require a Zone 0 designation. The final zone, Zone 2, is identical to its North American equivalent, Division 2. Explosive concentrations are not likely to exist in the atmosphere under normal operating conditions, but failure or abnormal circumstances could cause a temporary risk of a flammable atmosphere. While the intention of the risk categories is certainly clear enough, those with the responsibility for conducting site evaluations or plan reviews to determine which risk category should be assigned often prefer to use a more quantitative analysis. There are unofficial numeric parameters that frequently serve as guidelines in the classification process. When the occurrence of ignitable atmospheres exceeds 1,000 hours per year, the risk would be judged to be Zone 0. Locations that were considered to be Zone 1 could experience explosive atmospheres between 10 hours per year and 1,000 hours per year. And under this method, when the issues occur less than 10 hours per year, the designation would be Zone 2. Of course, these parameters must be adapted to local practices, experience, and circumstances. Since it has a very important impact on the equipment that will be selected for the application, the risk analysis or classification of the hazardous location must also include information about the nature of the hazardous material that could be present in the atmosphere. Gases, vapors, and flammable liquids are assigned to groups based on the similarity of their explosion characteristics to the typical material used to represent the group. Within the North American class and division system, Group A is represented by acetylene, Group B by hydrogen, Group C ethylene, and finally Group D includes materials comparable to propane. The zone system has a similar method for dividing these hazardous materials into groups using the same explosive properties, but the letter designations are the reverse of those used with divisions. And in this case, both acetylene and hydrogen-type materials are pulled together under the designation 2C. Materials similar to ethylene are Group 2B, and those that have explosive characteristics corresponding to propane are designated 2A. The Roman numeral 2, appearing before each letter, indicates that these groupings of gases and vapors are not the result of underground mining, The special requirements for mining use the Roman numeral 1. Arcing and sparking that could result from the normal operation of electrical equipment is certainly a potential source of ignition, as is component failure. But there are also many types of electrical equipment, lighting fixtures, for example, that can produce sufficiently high temperatures to become a source of ignition. For this reason, a full risk analysis must also include information about ignition temperatures of the gases and vapors that could be present. Both the division and the zone systems use identical temperature codes, although the zone system relies on fewer steps. Part 4. Methods of protection and equipment for gases and vapors. Recalling that the fire triangle brings together the three essential components for combustion to occur: fuel, oxygen in the air, and a source of ignition, it is now possible to begin addressing the explosion potential identified during the risk analysis. A variety of approaches are available for the design of these specialized electrical installations. These are made possible by the alternative protection techniques that provide equipment options for the specific hazardous locations. The range of protection techniques can restrict the presence of the combustible mixture, isolate or reduce the energy of the source of ignition, or safely contain or quench combustion that could be initiated by the electrical device. Within these general approaches, there are 4 basic concepts of protection, each with one or more engineering solutions. The individual solutions have been assigned a simplified type symbol to make identification and specification easier and more consistent. The first concept includes equipment that has been constructed taking extra measures to produce no arcing, sparking, or high temperatures. These are known as increased safety devices, type E. The use of additional clearances, spring-loaded terminations, and physical protection provide a method that can be applied to standalone terminal and connection boxes, or in conjunction with other methods, such as those used for controls, motors, and lighting fixtures. Another approach has been developed around the concept of containing, quenching, and safely venting explosions that could occur when ignitable mixtures come in contact with arcing or high-temperature equipment. This concept includes explosion-proof enclosures, a major technique used in the division system. The enclosures are engineered with more than sufficient strength to contain an internal explosion of a specified gas, and are then able to vent the products of combustion to relieve the pressure, but only after they've been sufficiently cooled to prevent ignition of the surrounding atmosphere. The same technique is referred to as flame-proof in the IEC system and is designated Type D. Explosion-proof and flame-proof technologies have the flexibility to be applied to a wide range of equipment. This is especially important because it includes high-energy and high-temperature devices where alternative protection methods may be difficult or impossible to implement. The adaptability of flame-proof technology also allows it to be applied at the individual contact level. Enclosing the arcing device in its own miniaturized explosion-proof chamber with a flame path for venting permits a broader range of materials to be used for the fabrication of the overall assembly enclosures. Also included within this protection concept is powder or quartz filling, type Q. This technique relies on embedding the electrical source of ignition in specially refined quartz sand or glass beads. This is clearly not for devices with open moving parts, but fuses, transformers, and limited volume sealed components could be afforded protection with sufficient quartz powder surrounding them. No explosion or flame would propagate beyond the enclosure because of the snuffing qualities of the sand. Although this technique may be a satisfactory solution for certain design problems, it is not among the most common protection methods used. The next protection concept depends on limiting the amount of energy available in a component to below the level that is necessary to initiate an explosive reaction in a flammable atmosphere. Known as intrinsic safety, Type I, this technique uses specialized low-voltage components within the hazardous location and additional signal conditioning components outside of the hazardous boundary or in flame-proof enclosures. This approach effectively removes the ignition leg of the fire triangle. Because of the exceptionally low energy levels allowed, intrinsic safety is generally restricted to control, sensing, reporting, and data applications. Each risk classification places different demands on the equipment and confines certain technologies to particular zones. In the case of intrinsic safety, there are subtypes that have been targeted toward the particular risk. Type IB is intended for use in Zone 1 and 2 applications. Type IA is permitted for use in Zone 0, in addition to Zones 1 and 2. The final concept employs designs and procedures intended to prevent the flammable gases or vapors from coming in contact with a potential source of ignition. Pressurization is an engineering technique that purges the combustible atmosphere from the apparatus enclosure and maintains positive pressure within the enclosure throughout the time that it is energized. Using blowers with a source of clean air, compressed air, or bottled inert gas, the positive pressure prevents the entrance of the ignitable material. The operating, pressure sensing, measurement, and alarm features that must work together to provide Type P pressurization can be quite complex. However, this can be the preferred method for creating overall protection in multi-component power and control panels, as well as entire control rooms. The subtypes PX, PY, and PZ indicate the level of reduction in the explosion risk achieved by each of the pressurization designs. Also within this concept is encapsulation, Type M, a fabrication technique that primarily provides protection for solid-state electronic components and several types of circuit boards. Certain sealed devices containing limited volumes with constrained temperatures may also be encapsulated. A variety of compounds, epoxy resin, for example, would be used in the initial fabrication process or in a potting procedure following assembly of the manufactured components. Similar to intrinsic safety, a second letter is used to identify the zone applications allowed for the equipment. MA is permissible for all zones. MB is for Zone 1 and 2, while MC may only be installed in Zone 2. An additional technique within this concept is oil immersion, Type O. Although a rarely used type of protection, there are some pieces of equipment that may present challenges that can be more easily overcome by using non-flammable oils to submerge the apparatus. The oil surrounding the device prevents the hazardous material from coming into contact with the source of ignition. It may also be called upon for cooling. Transformers and other static devices, as well as certain startup equipment, could employ oil immersion. Restricted breathing, designated NR, is a method of sealing and control for use in Zone 2 that has become particularly important in the design of lighting fixtures and other heat-producing devices. The extra measures used to prevent the entrance of gases and vapors from a short-duration flammable atmosphere that could occur in Zone 2 protect against developing explosive concentrations near elevated thermal points within the equipment. Testing for the temperature codes that will be assigned to the NR equipment can now be based on the cooler surfaces of the restricted breathing envelope. Both ATEX and the IEC differentiate among the types of protection to reflect the degree of ignition risk for each method. This is to clarify the zone for which each type and subtype is suitable. ATEX uses categories and defines Category 1 as equipment types with a very high degree of safety, including the anticipation of 2 independent failures. Category 2 provides a high degree of safety, even when a single failure occurs. Category 3 equipment would be designed with a normal or standard degree of safety. The letter G is used with the categories to make it clear that the degrees of safety are based on a gas or vapor hazard. The IEC uses nearly the same definitions for determining its Equipment Protection Level, or EPL. However, in the case of the IEC, the same letter designations are used for the different levels of protection that are also used for intrinsic safety and encapsulation. Equipment Protection Level A is a very high protection level. EPL-B is a high level of protection, and EPL-C is a standard or normal level. Again, the addition of the letter G indicates a gas or vapor hazard. An EPL of A may be installed in all of the zones. An EPL-B is not intended for use in Zone 0, but may be used in Zones 1 and 2. EPL-C is limited to Zone 2. This parallels the use of ATEX categories 1, 2, and 3. Each of the protection technologies is assigned an EPL for its highest safety level. Protection types intended for a particular zone may be used in a zone of lower risk. There is a consistent relationship among each of the risk assessment zones, protection types, and equipment protection levels for non-mining environments, where gases, vapors, or atomized flammable liquids could create explosive mixtures in the atmosphere. Part 5. Risk Analysis for Combustible Dusts. Another class of risk requiring assessment for explosion potential is combustible dusts. Referred to as Class 2 in the North American approach, finely milled, ground, or pulverized organic material, like wheat, wood, and coal dusts, can be just as explosive as gases and vapors when suspended in the atmosphere. Certain inorganic materials, metal dusts, for example, could also form ignitable suspensions. The North American system again separates the explosive risks into two divisions. Division 1 is where normal operations could produce an ignitable suspension of dust continuously or at least some of the time. In Division 2, it is unlikely that an explosive concentration of dust would occur during normal operations. Similar to the treatment of gases and vapors, the IEC creates 3 zones for risk assessment. Zone 20 covers risks of ignitable concentrations of dust that normal operations could produce continuously or for long duration. The risk in Zone 21 is considered less severe and is defined as an explosive dust suspension being only likely during normal operations. In Zone 22, the risk of ignitable concentrations is unlikely under normal circumstances, but it's possible that an accident in the storage or handling of the material, for instance, could generate an ignitable cloud. The characteristics of various dusts also require groupings in the assessment of their potential behavior. In the division system, Group E contains metal dusts. Because of the conductivity of metallic dust, there is a special assessment rule that they must always be designated Division 1 under the North American approach. Group F includes solid fossil fuels and or similar carbonaceous material, such as coal and coke dusts. Group G covers grain and other agricultural dusts that are created during the processing and handling of products like wheat, rice, and corn. The IEC also uses groups based on material characteristics. The groups assigned for dusts are preceded with the Roman numeral 3. Remember, this is part of the series where Roman numeral 1 identifies explosive byproducts found during mining, and Roman numeral 2 designates non-mining gases, vapors, and flammable liquids. Again, in seemingly reverse order from the division system, Group 3C includes conductive dusts. Group 3B covers non-conductive dusts and combines Groups F and G from the division system. Rather than finely pulverized dust, IEC Group 3A contains flammable fibers and flyings that might, for instance, be found in a woodworking plant or a textile mill. In these situations, the concern is more about an easily ignited and rapidly burning fire than an explosion. The buildup of fibers and flyings on electrical equipment might result in elevated temperatures that could be high enough to initiate an unexpected fire, or even lead to spontaneous combustion as the material ages under thermal stress. This particular IEC group incorporates and consolidates the North American treatment and classification of fibers and flyings known as Class 3. As with all aspects of dealing with hazardous locations, temperature information is critical to the risk management process and product selection. Controlled testing provides the essential data on the thermal behavior of the equipment. Part 6. Methods of protection and equipment for combustible dusts. A framework very much like the one used to explain and label the protection types used for gases and vapors has also been devised for dust environments. In fact, many of the gas and vapor protection types are also available to guard against the risks of dust explosion or fire from fibers and flyings. However, it is important to be aware that the actual protection mechanism may rely on a somewhat different concept for the dust risk than with gas and vapor. The fluidity and compressibility of free gases and vapors will permit their inevitable migration and seepage into spaces and equipment unless very specific and robust design measures are taken to prevent it. In contrast, the physical nature of dust permits a more inherent reliance on tightly assembled or firmly gasketed enclosures to seal dust away from electrical components. This increased dependence on dust-tight, dust-ignition-proof, and dust-protected housings to address the risk of explosive dust clouds, however, introduces additional thermal concerns. Despite maintenance and housekeeping programs that may be in place at dust-producing facilities, the assumption must be made that the combustible material could settle on electrical enclosures and apparatus. The resulting dust blanket could cause the internal devices to operate at elevated temperatures, even under normal operating conditions. Additional engineering considerations are required to deal with the impact of the dust blanket by both the equipment manufacturer and the user. The all-important dust protection by enclosure, Type T, is added to the table, along with the other now familiar protection techniques. Type T dust protection also has the added EPL of A, B, or C to designate whether the equipment is intended for Zone 20, 21, or 22. One additional but intuitive difference that is also quickly apparent in the table is that the designation G, used with the EPLs for application in the gas and vapor risk zones, has been replaced with the letter D for dust. Part 7. Ingress Protection, Preventing Physical Interference. The need to pay particular care to construction has always been integral to the design of explosion-proof and flame-proof enclosures. But many of the alternative protection types also depend on the design and integrity of the housing to prevent physical interference or the entrance of water or foreign matter that could defeat the equipment or component protection. In North America, designations such as NEMA 3 for rain-tight, NEMA 4 for hose-down, and NEMA 6 for submersible are typical of the environmental and physical protection ratings used for enclosures. Ingress Protection, or IP, is the rating system standardized by the IEC. It uses a 2-digit code to assure that the proper physical safeguards are in place for the EX protection type selected and its environment. The first digit following the IP designation denotes the extent to which the internal components are shielded from inadvertent or intentional access or foreign objects. The numbers range from a low of 0 with no physical safeguards provided up to level 6, which is fully dust-tight and prevents access even with a probe as small as a fine wire. The second digit signifies the degree of protection afforded against the entry of water. In this case, there are 8 levels of entry safeguards, ranging all the way through protection from continuous submersion in depths greater than 1 meter. Examples of typical ingress protection ratings would be IP54, for an enclosure that is protected from dust as well as water splashing from any direction, neither of which could enter in a sufficient amount to cause harm. An IP66 rating would mean that the enclosure would allow no dust to enter. It is fully dust-tight, and powerful water jets or heavy seas would have no effect. If the rating were raised to IP67, the enclosure would also be able to protect the equipment from immersion in shallow water for a short period of time, less than 30 minutes. Because the laboratory testing is not identical, and NEMA includes additional environmental factors, it isn't possible to exactly match NEMA protection types with IP ratings. But as a rough equivalent, the IP54 safeguards would be similar to NEMA 3, IP66 to NEMA 4 and 4X, and the IP67 would parallel NEMA 6. Part 8. Testing, Certification, and Quality Assurance. The effort to align with IEC standards certainly moves national, regional, and global installations toward a harmonized approach on risk analysis, classification of areas, and the specification of protection types. But there is one other matter that is directly impacted by this movement, and that is the certification of devices, components, equipment, and assembled apparatus. Prior to the drive toward harmonization, each country's recognized laboratory developed its own set of testing protocols to evaluate products. But the problem with this individualized approach is that it lacks the coordination to provide consistent assessment criteria and testing, and that undermines the goal of eliminating barriers to the international trade of explosion-protected equipment. The IEC EX scheme was developed to address this issue. The intent of the plan was to be able to provide a single global certificate of conformity based on uniform testing and documentation procedures. The scheme also included an assessment system to evaluate a manufacturer's quality program, procedures, and documentation, as well as assurances of continuing audits. While acceptance of a single certificate of conformity still remains the objective, it is a work in progress, with only a small number of countries currently accepting the COCs without additional local documentation. However, test reports issued by the laboratories certified under the IEC EX scheme are widely accepted as the assessment basis for the locally generated certificates. The assessment of manufacturing facilities, procedures, and internal documentation must also be conducted by an agency approved to conduct that appraisal. Known as a notified body, the Quality Assessment Report, or QAR, that they complete is an integral part of the product certification process. The actual product examination takes place in addition to the thorough testing that a company like Killark conducts on its own. It can involve explosion tests, hydrostatic pressure measurements, and thermal evaluations. Additional chemical resistance analysis, electrical performance trials, dust penetration reviews, and endurance trials would be included. Also, hose down, static discharge, and induced failure investigations, along with any other assessments that may be called for by the EX scheme, would be performed. Once all of the tests and analyses have been completed, they are reviewed by the agency's engineering staff, and then the notified body will endorse the QAR, and then issue the final test report and the Certificate of Conformity. The importance of the IEC EX scheme has continued to grow. 30 member countries are involved in the management of the IEC EX scheme, with more than two-thirds having one or more recognized laboratories. And with endorsement by the UN, even more countries are relying on the scheme. Part 9. Nameplates and Marking. Without doubt, quite a range of information is required in order to properly select and specify the protection methods, types of equipment, and precise products to be used in a location that has been classified as hazardous. Certificates and other documentation are absolutely important, but that information must also be easily available directly on the equipment for installation personnel, inspectors, maintenance crews, and field safety engineers. Indelible marking of the equipment to be installed is critical for these needs. The codes and symbols that have been assigned to each of the characteristics leading up to equipment selection must be assembled into a surface or nameplate marking consistent with standard IEC practice. As a point of reference, traditional North American marking uses a descriptive approach that includes class, division, and group, along with the manufacturer's name, location, and the certifier's mark. Depending on the product and the application, the NEMA environmental rating, as well as operating test temperatures, could also be required. One standard, one certificate, one mark is the harmonization goal, and significant progress has been made. Toward that objective, the IEC marking rules employ the codes and symbols in a specific and consistent format to fully describe the location and protection types that distinguish the product and application. But there are still some variations, even a few that may be redundant, in satisfying the requirements for different national and regional controlling authorities. Starting with the basic IEC marking, EX is used to show that the equipment is explosion protected. This is followed by the protection type, the equipment group, and then the gas or dust material group. Following that string is the temperature or T code. The actual temperature might also be included, if not redundant, with the other marking. Ingress Protection or the IP number could also be a required part of the nameplate. Of course, the manufacturer's name and location would also be included, as well as the Certificate of Compliance number. For products that also carry an ATEX certification, additional marking includes the use of Epsilon X within a hexagon to indicate that it complies with the directive. This would be followed by the equipment group, product category, and atmosphere designations. Conforming products intended to be placed in commerce for Senelec countries must also include the CE mark, followed by the identifier for the notified body responsible for the manufacturer's quality assessment. There have been several recent changes in marking procedures, and there are likely to be more as blending from continuing harmonization becomes possible. Despite the changes, the fundamentals will remain the same, providing for consistent interpretation in the application of explosion-protected equipment. Little doubt remains that worldwide coordination efforts under IEC standards will continue, and the goal of harmonization will be achieved. Killark, a division of Hubbell Incorporated, is an internationally recognized manufacturer of electrical construction products, equipment, and systems for hazardous locations and global applications. Come to Killark.